Hello students. Hello and welcome to this video. In this video, we will finish the remainder of theory and we will solve 10 questions. So without further ado, let's get started. The link to download the PDF will be in description, as well as at the end I'll show you how you can download the books from the website to maintain an updated copy and the question answer website which I have prepared for you. So first we have fractional index for binomial theorem. We let f of m is equal to 1 plus x to the power m is equal to 1 plus mx plus m into m minus 1 by 1 into 2x square plus m times m minus 1 times m minus 2 upon 1 times 2 times 3 x cube, which is the typical binomial expansion for positive integer, which we have already proven. This is MC0, this is MC2, MC3, and so on. Now, all this means m is in the set of real numbers, then f of m can be written similarly here, and f of m times f of n is equal to 1 plus x to the power n plus 1, which is f of n plus n. So, f of m into f of n to k factors is equal to f of n plus n to k factors. Now, we let m and n each equal to j upon k. So, f of j upon k to the power k is equal to f of j. Okay, so here it will become f of j upon k to the power k, and here it will become f of j because we have n plus n all the way to the end. But j is a positive integer, so f of j is equal to 1 plus x to the power j. So 1 plus x to the power j upon k is equal to f of j upon k. So 1 plus x to the power j upon k is equal to 1 plus j upon k x plus j upon k times j upon k minus 1 divided by 1.1 times 2 x square and so on. And that is the binomial theorem for negative index. Now for the negative index, we have f of n times f of minus n is equal to f of 0 is equal to 1 from this relationship. Okay. So f of minus n is equal to 1 upon f of n, that is 1 plus x to the power minus n, which is equal to 1 minus nx plus n times n minus 1 upon 1 times 2 x square minus so on. Now we have binomial theorem for general term and binomial theorem for any index. General term is given by n times n minus 1 and so on up to n minus r plus 1 over r factorial times x raised to the power r. The above expansion does not hold true when mod x greater than 1, which can be quickly proved by making r arbitrary log. For example, 1 minus x to the power minus 1 is equal to 1 plus x square plus x cubed. However, if you put x is equal to 2, we have minus 1 to the power minus 1 is equal to 1 plus 2 square, which shows that when x is greater than 1, the above formula does not hold true. From geometric progression, we know that 1 plus x square up to r terms is 1 upon 1 minus x raised to the power r by 1 minus x. Thus, if r is very large and mod x less than 1, we can ignore the second fraction, but not when mod x greater than 1. Now we have general term for negative index. The r plus 1x term is given by minus n times minus n minus 1 and minus n minus 2 up to minus n minus r plus 1 over r factorial times minus x to the power r, which is equal to n times n plus 1 times and so on up to n plus r minus 1 over r factorial times x raised to the power r. Now we have some exponential and logarithmic series expansions. Logarithm spelling might be wrong. Yeah. Following expansions are useful for solving problems related to exponential and logarithmic series. So A is missing here. E raised to the power x is equal to 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial up to infinity, where x is any number, E lies between 2 and 3. If a greater than 0, a to the power x is equal to e raised to the power x times log of a with base c is equal to 1 plus x log of a with base c upon 1 factorial plus x log of a with base c whole square upon 2 factorial and so on. And log formula we have already seen, log of 1 plus x with base c is equal to x minus x square upon 2 plus x cube upon 3 minus x4 upon 4 and so on. up to infinity, where x lies between -1 and 1. Now we will solve some questions. So let me open the solution here. So we have this. Okay. So first question is expand x plus 1 upon x raised to the power 5. So we expanded 5c0 x to the power 5 plus 5c1 x to the power 4 times 1 upon x plus 5c2 x times 1 upon x square. This should be x to the power 3 actually here. There's a mistake here. Then 5c3 x square upon times 1 upon x cube plus 5c4 x times 1 upon x to the power 4 plus 5c5 1 upon x to the power 5, which is equivalent to this. So powers of x get cancelled. They decrease by 2 because x is decreasing by 1 and 1 by x is increasing by 1. We have x to the power 5, x to the power 3, x, 1 upon x, 1 upon x cubed, 1 upon x to the power 5. Second question is, use the binomial 7 to find the exact value of 10.1 to the power 5. So 10.1 can be written as 10 plus 0.1 to the power 5. So it is 10 plus 1 upon 10, which is similar to this fraction. So the final value will have expansion like this. So we have 5 is 0, and this is, there should be 5 zeros here, there are 4 here. Should be 5 zeros, 1 zero is missing. Over here it is correct. And then we have 1000, then we have 10, then we have 1 upon 10, then we have 1 upon 1000, then we have 1 upon 100,000. So here it is 100,000 plus 5,000 plus 100 plus, there should be one more zero here again. Okay, so, no, this is fine. 100,000 is fine. Zero is missing here. Okay, then 100, then 1, then 0.005 plus 0.00001. So we add this and we finally get this. The sum is wrong actually. It is incorrect. I'll fix this problem. Okay? So 100,000 plus 5,000. So 105,101 plus 0.005001. 00501. Yeah. Okay. Now next question is simplify x plus square root of x minus 1 raised to the power 6 plus x minus square root of x minus 1 raised to the power 6. So we simply expand it, we get 6c0 x to the power 6, 6c1 x to the power 5 square root of x minus 1, 6c2 x to the power 4 times square root of x minus 1 whole square, and so on up to we have 6c6 square root of x minus 1 to the power 6. And when we expand, alternate terms will have a negative sign for the second one. So the alternate term 6, this term will cancel, this term will cancel, and this term will cancel. So what we are left with 2x to the power 6 plus 30x to the power 4 times x minus 1 plus 30x square x minus 1 whole square plus 2 x minus 1 whole cube. Question 4 says that if A be the sum of odd terms and B be the sum of even terms in the expansion of x plus A raised to the power n, prove that A square minus B square is equal to x square minus A square whole to the power n. So we consider the expansion of x plus A to the power n and x minus A to the power n. So we have x plus A is equal to nc0 x to the power n plus nc1 x to the power n minus 1, and so on, which will be equal to A plus B, because A is the sum of odd terms and B is the sum of even terms. So entire thing will be A plus B. And x minus A to the power n will become A minus B. So multiplying, we have x square minus A square raised to the power n is equal to A square minus B square. Question 5 says that if n is a positive integer, prove that the integral part of 7 plus 4 square root of 3 to the power n is an odd number. So we let 7 plus 4 raised 4 square root of 3 times square root of 3 whole to the power n is equal to alpha plus beta, where alpha is a positive integer and beta is a proper fraction. Now clearly 0 less than 7 minus 4 square root of 3 less than 1. You see that from this formula. Okay. So we raise this to the power n is equal to beta 1. We let this equal to beta 1. Now beta 1 will lie between 0 and 1. So alpha plus beta 1 is equal to 2 times. We add this and this. We get 2 times 7 to the power n plus nc2 7 to the power n minus 2 into 48 and so on, which will be equal to an even number. Now beta plus beta 1 is equal to an even number minus alpha, that is an integer. Okay. Now beta and beta 1 lies between 0 and 1. So beta plus beta 1 will lie between 0 and 2. Thus beta plus beta 1 is equal to 1. Now alpha plus 1 will be an even number and hence alpha will be an odd number. Now that is question number 6. Question number 7. Now question number 6. If 7 plus 4 root 3 to the power n is equal to alpha plus beta, where alpha is a positive integer and beta is a proper fraction, then prove that 1 minus beta times alpha plus beta is equal to 1. So we reading from the previous problem, we have alpha plus beta times 1 minus beta is equal to alpha plus beta times beta 1. So that is equal to 7 plus 4 root 3 to the power n times 7 minus 4 root 3 to the power n is equal to 1. So that is the answer which we have. Question 7 says that find the coefficient of 1 by y square in y plus c cube by y square raised to the power 10. So general term is 10 cr y to the power 10 minus r c cube upon y square to the power r. Now coefficient of y square is 10 minus r minus 2r, that is equal to minus 2. So r is equal to 4. So coefficient is 10 c4 times c to the power 12. Question 8 says that find the coefficient of x to the power 9 in 1 plus 3x square plus x cube to the power 15. So this is 1 plus x whole cube. So right hand side becomes 1 plus x to the power 45. Therefore, coefficient is 45c9. Question 9 says that find the term independent of x in 3 by 2 x square minus 1 upon 3x to the power 9. So here we write the general term which is tr 9cr minus 1 3 by 2 x square to the power 9 minus r plus 1 times minus 1 upon 3x raised to the power r minus 1. Now if you see power of r here, it will be 9 plus 1 is equal to 10. 10 times 2, 20. 20 minus 2r. And this would be equal to 1 minus r because this is in denominator. So total will be 21 minus 3r is equal to 0 because the term is independent of x. So r is equal to 7 and coefficient is minus 1 to the power 6, 9c6, 3 by 2 raised to the power 10 minus 7 times 1 upon 3 to the power 6 is equal to 7 by 18. Question 10 says that find the term independent of x in 1 plus x to the power m times x plus 1 upon x to the power m. So we write this as x to the power minus n times 1 plus x to the power m plus n. So you take LCM, it becomes 1 plus x to the power n upon x to the power n. So we have x to the power minus n. Now to find the term independent of x in the expansion, which is coefficient of x to the power n in 1 plus x to the power n plus n, which is equal to m plus n, c n is equal to m plus n factorial over n factorial times n factorial. And with this, we come to the end of first set of problems on binomial theorem. Now I'll show you my website, ashtavaku.org. You can download algebra, trigonometry, and coordinate geometry PDFs from here. So when downloading, you download and add the date which is mentioned here because the links do not contain date themselves, because if I put the date there, then whenever the date changes, old links will become invalid. Now there may be typing mistakes, quite a lot of typing mistakes as you have already seen. Now, so study with the piece with care that there is typing mistake. Now, if you look at the question answer website, that is the eighth link, okay, Kunjika. So you come here and you make a login. There are some people already here, so you make a login and ask questions. In order to learn how to do Markdown editing, because we will need that, we go to Markdown help and read this piece of documentation, and you'll be fine. Okay. So feel free to make a login and ask questions here. So with this, I will end this video here and we'll meet again tomorrow with 10 more problems on binomial theorems. Thanks a lot for watching the video. Have a great day ahead and enjoy.